Good afternoon. As that first slide outlines to you, this evening we'll focus on organic content, so primarily the Unit 2 content, okay, and that will also be the content of my next week's session as well. So naming organic compounds specifically, we need to go back to the roots of what you came across in Key Stage 4. So during year 11, if you remember, if you're doing double award, it would have come into that final unit you did, which was the crude oil unit. And then if you did the triple award in separate sciences, then it would have been the unit just before the final one, because obviously there's 6 units in the separate syllabus. Okay, so naming organic compounds. Let's first make sure that you are familiar with the array of families that you need to be familiar with for year 12. Okay, so in organic, there are some repetition from what you did in Key Stage 4. So obviously you have to be familiar with alkanes, which we came across in year 11, alkenes in the same way. As a new family this year, the halogenoalkanes. Now, you will come across that called haloalkanes in some literature, but for the WJC, it is actually called the halogenoalkanes. Alcohols, again, is familiar to some of you from Key Stage 4, but not all of you. Okay, so the alcohols, the carbonyls, which is a brand new family, carboxylic acids, and then leading on to the final family, which are the esters. Okay, so I'll run briefly through all of these for you this evening, just so you're a bit more comfortable in being able to recognize them and as a result being able to name them. Okay, so alkanes probably start you off in the most comfortable family, because it's the one that everyone studied in quite some depth in that final unit, so the oil unit. So alkanes. Now, alkanes are compounds that are classically one of the 2 hydrocarbon families you came across in year 11. So it consists solely of the carbon atoms and hydrogen atoms. Okay, so they're called hydrocarbons, and the chemical structure of alkanes are what we classify as saturated. Okay, so because they only contain single bonds, they're described as saturated. So this is because they contain those single bonds and nothing else. So they satisfy this formula which you came across in year 11. Okay, so the general formula for an alkane as a hydrocarbon means you simply take the number of hydrogens, you double it, and you add 2. So if you want to work out what the formula of the 107th alkane would be, simply double 107 and add 2. Okay, so it is well worth being able to recall that generic formula of CnH2n plus 2, because sometimes you'd be asked to recognize or differentiate between families, and often the only evidence that would suggest that it is either an alkane or an alkene is whether or not you've got the correct number of hydrogens. So alkenes, again, familiar to most of you. The only thing that has really been built upon during year 12 content, if not done already, will very quickly be done by your teacher, I'm sure, is that alkenes don't have to be a single double bond. So in GCSE, not that it was a lie in a sense, but we did not emphasize potentially the fact that alkenes can have multiple unsaturated regions. Okay, so alkenes, again, as a hydrocarbon family, so consists only of these carbon and hydrogen atoms. But it does, and this is the key thing, that's where the progress is that to classify as an alkene, you have to have 1 or more carbon-carbon double bonds in your structure. Okay, because of that double bond, it introduces this nature which we describe as being unsaturated, because carbon, being in group 4, should in theory be able to saturate itself by bonding to 4 different things. But in an alkene, because it will only ever be within that double bond bonded to 3 other things, then it's described as being unsaturated. Now, the unsaturated nature in GCSE, we said, meant that it led to the generic formula being simply CnH2n. So we encourage you to work out the number of carbons and double it, and that would tell you the number of hydrogens. Well, that's no longer true. It can be true, but only in a single double bond presence. So be careful in using this generic formula a bit too much, okay, because it only applies if you've got a single double bond. Okay, that's misleading in itself, really, isn't it? Saying single double bond, but it means you've only got a double bond present once within the compound itself. If it's got multiple double bonds, then it has even less hydrogens than what you'd expect. So be careful with that one. Okay. The third family was a very simple adaptation, I suppose, of the first family, which is the alkanes. So halogen alkanes, as you know from Key Stage 4, halogen is any member of group 7. So it simply means that you substitute one of the hydrogens on the hydrocarbon chain with a halogen of your choice. It can be multiple halogens present, and it can be a range of halogens. You can have a substitution of a single hydrogen. You can substitute multiple hydrogens, and you can also substitute more than one halogens within the same molecule. Okay, so halogenoalkanes is an alkane with one or more, and this is the key thing. Don't get sidetracked by thinking it's a single halogen. It can be multiple halogens bonded to it. Halogenoalkanes contain one or more of either fluorine, chlorine, bromine, or iodine, therefore, directly connected to the hydrocarbon. But because in a hydrocarbon, it is always the carbon that has multiple bonds. Hydrogen can only ever bond to one thing. Within a halogenoalkane, that halogen will be directly linked to the carbon and nothing else. Okay, so a classic example, I suppose you could say there's 2-chlorobutane. So take the name, break it down. Bute, and I'll cover this in a much more smaller steps in a minute though, but bute, I'm hoping you can recall from year 11, simply suggests 4, the presence of 4 carbons. Then it suggests that at point 2 of that chain, something must be happening, and what's happening is that you are substituting or adding on a chloro. Okay, so if you look at the structure, we've got 1 carbon, 2 carbon, 3 carbon, 4, which therefore, circle 4, which suggests therefore that you've got 4 carbons, hence the bute. And on position number 2, because that would be position 1, that would be position 2, you clearly got a chlorine. So as a whole name, that would be 2-chlorobutane. Okay, right. The next family you have to be familiar with, again, it is a bit more comfortable for the triple or separate students from GCSE, because you would have studied ethanol as part of the same unit I was talking about earlier, which is the crude oil one, but it was an additional section to that crude oil unit. Now, alcohol suggests that you've got a carbon chain and you've got a hydroxy or an OH group attached to one of those carbons. Okay, now these alcohols can either be described as being primary, secondary, or tertiary. It is crucial that you are confident in being able to work out and allocate a correct label. So if you see or you're given an alcohol, that you can work out whether it is one of these primary, which we're quite lazy in chemistry. We have shorthands for most things. So we represent primary with that, secondary, and then tertiary. Each one has a criteria to be described as what it is. Okay, so let's start from the beginning. The primary alcohol. So primary alcohols are any alcohol which has that hydroxy OH group attached to the terminating carbon. So that means it's at the end of the chain, or in the case of methanol, where there's only 1 carbon anyway, it would be still described as being terminal. So that hydroxy group, the OH, is terminating carbon, has got the OH attached to it. So the last carbon on any carbon chain. So it can be any length, but as long as that OH is at the end of a chain, it's still described as being primary. Do not assume that it's a single carbon. I've seen that in rare occasions, but I have seen it where people assume that if it's a primary alcohol, you're suggesting that it's a single carbon. It's not. It's linked to the location of the carbon within that chain itself. So prop, as we'll cover in a minute, but prop, if you remember from GCSE, is a 3-membered chain. It's telling you that it's on the first carbon, again, reminding you that it's a terminal carbon. So propan-1-ol is a primary alcohol. Okay, right. Then you've got secondary. Now, secondary is described as being secondary if the hydroxy group, so the alcohol group, is attached to 2 other carbon atoms. So the OH, whichever carbon it's attached to, has a carbon chain either side of it. So it has at least 2 other carbon atoms in that chain. Again, be careful with seeing this a lot more frequently, so a lot rarer, so not as rare, sorry, is that I see lots of people assuming that a secondary alcohol means that it's located on the second carbon of a chain. A secondary alcohol can be 100th carbon in the middle of a huge chain, but as long as it's in the middle of a chain with a carbon atom either side, then it's still classified as secondary. So don't get misled by that too. 2 simply means attached to other carbon atoms, not on the second carbon itself. Okay, so an example in this case, we stick to the prop, which means 3. Instead of having that hydroxy OH group at the end or terminal carbon, we have it centrally. Okay, so that would be propan-2-ol. So you have it as it sees there. That's carbon number 1. That's carbon number 2. That's carbon number 3. And you can see that the hydroxy OH group is attached to the central one there. Okay. Tertiary, if you use that rationale I've just explained, terminal or has 2 carbons either side of it, let's ramp it up to the next step. So tertiary alcohol simply means that the alcohol group, okay, is attached to a carbon with 3 other carbon atoms also attached to it. So it's got no hydrogens on the same carbon as itself. So the OH group has no hydrogens on that carbon that it's branching off of. So the classic example would be 2-methyl-butan-2-ol. So if you look at butan, it would be 4-membered long. On the second one, you'd have a methyl coming off of it, and the OH then on the same second carbon. Okay, so be careful that you don't, as I say, confuse the 1, 2, and 3 with anything more complicated. It simply means how many other carbon atoms are attached to the same carbon as the hydroxy group. Now, carbonyl, this is a brand new group for you this year. So carbonyl is something that was occurring, but unbeknown to you in GCSE. It's the family that often lies between alcohols and the carboxylic acids that you would have come across when you're discussing how these bacterial oxidation of alcohols makes it taste vinegary after a period of time. So carbonyls is like a halfway house family where they get formed, but often can then further oxidize. Not always, but can further oxidize onto another family. So carbonyl group is a chemically organic functional group composed of a carbon atom which is double bonded to an oxygen atom. So it contains a C double bond O. Now, there are 2 families that are within this generic family of carbonyl, and they're called aldehydes and ketones. Now, they're simple compounds which contain that, as I say, C double bond O. They're simple in the sense that there's nothing else attached to the same carbon. So there's nothing like an OH attached to the same carbon as the double bond O, which is a functionality you would associate with an acid. Okay, so it's simple in the sense that the carbon we're talking about only has that C double bond O to kind of deal with. So there's no major complexity to this family. Aldehydes, as you can see there, we've got the presence of this group which we're talking about, okay? But in each case, to be an aldehyde, that carbonyl group is terminal, so it's at the end of a chain. So in aldehydes, the carbonyl compound has a hydrogen atom attached. So you can see there's a hydrogen attached to the same carbon in each one of these cases, okay? So aldehydes has a terminal location within an organic compound. Okay, ketone means that the C double bond O is not terminal, it's central to a chain somewhere. So you've got a C double bond O, again, same functionality, but now if you notice there's no H attached to the same carbon as the carbonyl group itself. So there's an alkyl group either side of it. Okay, so ketone means that you've got the carbonyl with 2 hydrocarbon groups attached either side of the carbon we're discussing. Carboxylic acids, again, familiar to some of you from GCSE, but possibly not all of you. So a carboxylic acid is an organic compound that includes what I call the COOH group, so COOH, okay, in its chemical structure. So pentanoic acid, ethanoic acid, which is the constituent ingredient in vinegar, okay. So it simply means that you've got the functionality of a carbon. So again, it's terminal we're discussing here. It's got a double bond O attached to it, and then it's got an OH. Okay, so it contains the COOH group, the COOH. So esters are not very thoroughly studied in year 12. It's much more in-depth studied in year 13, but it is a condensation product of a alcohol reacting with an acid. Okay, and it's called condensation because if you notice, the carboxylic acid has the functionality of an OH, as you can see there, and alcohol also has an OH, but only concerned with the hydrogen of the alcohol itself. And what it does is that it condenses out. So what you get is that it gets rid of that water molecule from the central join, which appears here. And then you have what is called an ester link. Now, ester links are something that are thoroughly studied in biology as well. So if you are studying more than one science, i.e. biology as side by side with chemistry, then you'll find this will be useful in biology and vice versa. So there's a bit of crossover content between biology and chemistry in this sense. So esters condense. It's called condensation because you get the evolution or giving off of a small molecule. But it's always between, for the purpose of year 12, it's always between an alcohol and a carboxylic acid. Okay. Now, I'm not going to dwell too much of it because you've seen me play about with some of these formulas anyway, but it's really important that you are confident in being able to represent formulas in a multitude of ways. It's also crucial that you only give the formula in the desired or requested format. So sometimes they'll ask specifically for one type of formula to be the represented way. And if you give another representation of it, even if it's scientifically correct, you wouldn't get the credit. So be careful reading what will be short, sharp, single mark questions potentially, that you are confident in identifying these. Okay, so there are a number of ways to represent the same formula. Okay, especially if you go into more complex and larger molecules. For year 12, it's as simple as chains, but in year 13 and beyond, you've got ring systems as well, which are called aromatic systems. So to represent a formula, sometimes you need a bit more complexity than simply a molecular formula. So it tells you how many ratios of hydrogens to carbons, etc. you have. So sometimes that's not good enough and it's not very informative. So each formula has its own use and you must be able to write any compound in any of the formats stated. Okay, so the purpose of showing this, if we look at propane then, C3H8, which is a member of the first family, probably the easiest one to recall. So if you stick to propane, has a formula C3H8. Okay, so the molecular formula, that is what we'd call that. Can be useful and can be representative and enough to identify it, but not always. Okay, so the molecular formula simply shows the number of each atom in the molecule. It can be found from an empirical formula, which is the kind of calculations you'd have done in Key Stage 4. Okay, and combining that with a molecular mass. So if you know the MR and you know the ratio of atoms to each other, then you can calculate therefore and work out the molecular formula. General formula. Now, as I said, we've already had these for things like the alkanes. Alkenes is a bit of a dodgy one now because obviously you're aware of the possibility of having multiple double bonds present. But the general formula can be useful in some cases, especially if you're asked, do you think that this unknown X is an alkane or an alkene? Okay, general formula will be priceless in that case because if you can work out it's got double plus 2 number of hydrogens, then that tells you it's an alkane. Okay, so general formula doesn't have a massive use, but it does serve its purpose at specific times. Okay, so it shows the ratio of the elements within the compound of any series that you need to be familiar with this year. Displayed formula, this I like, okay, because it does what it says on the tin, okay? It shows you and displays to you in detail exactly what bonds are present, the nature of that bond, so it's very clear whether you're dealing with a single bond or a double bond, so is it saturated or unsaturated, and it shows you exactly what you're dealing with. So displayed formula can be a bit faffy, it takes a bit longer to draw, especially if it's quite a large molecule, but there's no doubt that the displayed formula is superbly useful. Okay, so this shows every atom and every bond in the molecule, and it is very quick then to identify saturation or unsaturation within any organic molecule. Structural it's a bit like a displayed, I suppose, but instead of drawing it, you simply list what's present in each carbon. So you take each carbon in order. So it's like the shorthand version, I suppose, of the displayed formula. So you write each carbon in order, what is attached to it, go on to the next one, what is attached to it. So stage 3, stage 2, stage 3, it's a shorthand version. It's not that much shorter though, so some would argue what's the point. Now this is very much a fast one, but is often mistakenly drawn, okay? Skeletal is very basic, but can be informative if you interpret it correctly. So skeletal in this case shows you the carbon skeleton. So only shows you the carbon skeleton as simple straight lines. So in this, if you think about each end of the line, so if I start here, that is carbon number 1 located right there. That's carbon number 2, that's carbon number 3. So if I wanted to represent something like, I don't know, pentane, okay? Put your pen down, you'd go 1, 2, okay, is the end of that. So 1, 2, 3, 4, 5. So basically zigzag it for however many lines you need to represent that, okay? So skeletal shows a skeleton of it, hence the term skeletal formula, but anything that branches off of that has to have a bond. So if it's an alcohol, you'd actually have to show an OH coming off of it. Be careful though, there is no carbon there. So no carbon at that point. Okay. Right, so that's skeletal. Hopefully that makes sense to you and you're familiar with these now and you're growing confidence in how to represent them maybe. Okay, if I go back to the next one then you've got the next one, which is 3-dimensional. This plays a part, if you think back to, I think it was Mr. Black's session last week, in fact, where he did the VSEPR. So 3-dimensional shows you not only what is present and what's bonded directly to each other, but it also gives you a representation of the shape it would orientate itself into according to the VSEPR theory. Okay, so valence shell action pair repulsion theory means that they are hardly ever planar. Most organic compounds aren't flat because what happens is that the atoms will repel each other because of the electron clouds. So they orientate themselves into a 3-dimensional shape to minimize that repulsion. So you can represent it with a 3-dimensional formula as well. Okay, or empirical, the final one I want to cover with you, which is very similar to the molecular and sometimes it's exactly the molecular. But if the molecular formula can be broken down into a shorter or smaller ratio, then that is classified as the empirical. So it's the simplest or lowest ratio of the atom within any molecule. So if I say, right, let's do the same for the alkene propene. Okay, so let's go for the first one. If I want to do the molecular formula and it's propene, let's assume that it's a single double bond. Then the molecular formula will simply be doubling the number of carbons, so C3H6, and it's 3 because of prop. Okay. General, well, we've identified as an alkene. It's not, I'm very cautious with this one, I suppose, because it's only true for a single location for an unsaturation, so it can be multiples. So, but for carrying through the GCSE knowledge, the general formula would be CnH2n. Displayed, you'd actually have to show every single bond. Being very clear, if you notice here, that's a double one and that's a single one. Okay, which is why I am an avid fan of displayed, because you can't go far wrong really, because it's literally showing you everything that you could potentially need to know to be able to name things and describe any bonding in it. Structural, take it each one in order. So you can see there's the first carbon and it's got 2 hydrogens attached to it, so CH2. Let's go on to the next one. I've got a C here with 1 H, so it's just CH. And then the last one you can see is this carbon. It's got 3 hydrogens attached to it, so CH3. So it's like building blocks, it's like Lego blocks, put it all together. Okay. Skeletal, well, it's a chain of 3. Okay, so let's just, as I said, you put that down, 1, 2, 3. It's an alkene, therefore one of those needs to be double bonded. Okay, so it's as simple as that. Let's get rid of that because I think I've got a more neat diagram to show you, which is always better. So skeletal simply means you've got 3 in a line, but one of them is double bonded. three-dimensional. Because of that unsaturated location, its shape can be a bit complex, okay, but three-dimensional one, that is what it would look like, okay. And then you've got empirical. Well, if you look at the molecular formula, yes, it can be broken down into smaller ratio because 3 will go into 6, and it can be broken down into CH2. That's the empirical, therefore. Right, you have to, as you did in GCSE, be able to name various chain lengths as well. Now, you have to be familiar with up to hex in GCSE, but you have to know a few extra ones this time as well, okay? So you've got the 1 carbon, which is meth, which is a single carbon. Then you've got eth, which is 2. 3 is prop or prop. You've got 4 carbons, which is but. You've got 5, which are pents. And then you've got hex, which is 6. Beyond that, though, you didn't really need to know it for GCSE, but most of you would have come across a few of them anyway, especially when you're discussing petrol, which is octane. But 7, hept. Some of them are more logical and linked to maths. If you notice, most of you are familiar with pentagons, aren't you? So that's an easy reference to make. I'm always trying to give my pupils references in their heads. Hexagon, 6-sided shape. Heptagon, 7-sided shape. Okay, so try linking these to maths if it helps. Then you've got octagon. Okay, oct, therefore, is 8. Non, not quite so easy to remember, but 9 is non. And then you've got decades. Decagon, 10-sided shape, so 10 carbons would be dec, okay? Right, now this again is something, isomerism, which I need to be clear on. You did come across it in year 11, but if I was honest, I often think my year 11s wing it a bit when it comes to isomerism. They tend to learn it parrot fashion without really thinking through what we're dealing with, okay? So isomerism, let's first recap what isomer means. Well, isomer means you've got different compounds, but they have something in common between them. So they could be the same molecular formula, but different structural formula, okay? So sometimes more than one type of isomerism can even occur within the same molecule. So the more carbon atoms there are, the more complex it can potentially be, and the greater number of possible isomers there are within that compound or formula, okay? So structural isomerism is caused by having different arrangements of carbon skeletons. So you've got straight chains, which means you've got all the carbons in exactly that, a straight chain. Don't forget, a straight chain doesn't have to be straight though. Okay, going around a corner doesn't mean that it's not straight, and I'll come back to that in more detail in a minute or two. They've got very similar chemical properties though, do structural isomers. They do have slightly different physical properties though, and it tends to be linked again to attractions and repulsions within a molecule. The more branching you have within a molecule, the lower its boiling point is, and that's simply due to the fact that you can't get them as close to each other because of the bulkiness of these branching, and the intermolecular attractions therefore don't take place so strongly, okay? So if I look at the classic one you had to know for GCSE, all of you, be it double award or triple award, and you're doing higher, you have to be able to get your heads around the different forms of C4H10. And instinctively, people go, well, that's butane. Okay, it's got 4 carbons and it's got 10 hydrogens, so it's an alkane of 4-membered long, so it's butane. It must be butane. Well, butane is one possibility, as we know, okay, but it's not the only one. Okay, so there are 2 versions or 2 ways you can represent 4 carbons and 10 hydrogens and be very different. So the first one, as I say, let's put them all in a straight line. But alternatively, and the advice I tell you then if they ask you to sketch structural isomers is take it down 1 carbon at a time. So if I put 4 in a row, great. Let's take it down. So the maximum I've got in an unbroken chain is 3. Okay, and that's what happens here, is that you have, as you can see, you've got 3 carbons in a row there, which means that suddenly the name in the is prefixed with prop because it's 3 carbon membered chain as the longest chain. And then on position number 2, you can see there, that's the second carbon of the 3 in a row. I've got another carbon coming off, which represents a methyl group. So the second isomer is called 2-methyl propane. Okay, so I always take this advice of take 4 and then take it down 1 and then take it down 1 if possible again. Okay, so if I look at C5H12, logically, I'm hoping you'd all go, right, okay, instinctively, I'm going to put 5 in a row. Excuse me for being lazy. I do this. Anybody that's ever been taught by me will know I tend to not put the hydrogens in because I'm lazy that way. Okay, so that's definitely one isomer that we need to be thinking about. Put them all in a straight chain of 5. Okay. What else am I going to do? Right, let's take it down one membered then. So let's take the second one and I'm going to put it as 4 in a row. I've got a 5th carbon I need to stick somewhere. Where can I possibly put it and it be different to number 1? Well, let's just put it on number 2 then. Okay, so let's put a carbon there. Now, alternatively, somebody is likely then coming, right, I'll not put it on number 2, then I'm going to put it on number 3. Okay, and they might show it as a chain of 4 and they'll put a C there because that's different. Yes? Well, the reality is no, it is not, because in organic chemistry, you have to get into the habit of naming things from the shortest possible side. Okay, so in this sense, you'd start from this end here in the first representation. That would be carbon number 1 and that would be carbon number 2. But in the same sense, you can number 1 from this side and that would still therefore be number 2. So the naming of the one would be carbon number 2, so 2. Coming off of that is 1 methyl. And then the longest chain is 1, 2, 3, 4, which means it is a butane skeleton. So it's called 2-methylbutane. For some weird reason, this is going a bit mad. Oh, it rubbed out the wrong thing. Apologies for that. So on the second carbon, so hence the 2, it's 1 carbon coming off, so methyl. And then the longest chain, as I said, is 4, so we call it a carbon chain of butane. Okay, so that's one extra way of doing C5H12. Is that it? No. In reality, there is a third one that we could be dealing with. So instead of having 4, let's go for 3. Okay. Instinctively, the first thing that people tend to then do is go, right, let's stick the 2F I've got left over and let's put both of them on the center one. Well, the problem with that is that now the longest chain is still 4. I know it doesn't look like a straight chain because it's going around a corner, but that is still an unbroken chain of 4 carbons, isn't it? 1, 2, 3, 4. And that's a single branch, again, on carbon number 2. So that's not the representation we want, okay? So the representation we need is 3 in a row, but somehow having the extra 2 coming off differently. So what we have here is that we have a C there and a C going up. And because it's one going up and one going down, it is a different representation. It's called the crucifix isomer. And it's called, the longest chain is 3. So we're going to end with the name prop or propane. Now what happens is that you've got carbon number 2, the central one there, and you've got 1 methyl coming off, but you've also got another methyl. Do not be tempted to call it an ethyl branch because an ethyl is 2 carbons in a row coming off. This is 2 separate methyls. So it's called 2,2. And we call 2 things of the same nature in chemistry di, like carbon dioxide. So it's called 2,2 dimethyl propane. Okay, so it's all about taking the little bits of information and building it into a bigger picture. So the difference between them physically, things like the boiling point and density are somewhat similar, okay, but they wouldn't be identical. Okay, so there is differences in their boiling point and densities to do with the fact that there'd be weaker intermolecular forces. So to explain that, the straight chain isomers have higher values than branched ones because you can get them closer together, and the closer they become, the more attracted they become to each other. So we call the intermolecular, it's like an international rugby match, I tell my pupils. never football, it's always rugby. So branching stops them cutting together or getting as close to each other as possible, which means the intermolecular forces are then weakened. And the weaker the intermolecular forces, the lower the boiling points become. So as a result, if you compare the two isomers there of C4H10, the straight chain butane has a boiling point of minus 0.5. Okay, so just beneath freezing point of water, so 0. But the branched one, it isn't a huge difference, but you can see that there has been a dip in that boiling point. So suddenly the branched version, the 2-methyl propane, has a boiling point of minus 11.7. So the greater the number of branching as a general rule, the lower the boiling point will become because those intermolecular forces are weaker. So the molecule has the same carbon skeleton, molecule has the same functional. So this is the second type of isomerism we need to think about now. So it's called positional. Okay, so you're taking the same functionality like we did earlier, like halogenoalkane or an alcohol, but instead of putting it on a single location, there is potentially more than one place you can put it. Okay, so example, if I go for alkenes, if you've got a chain of 4 or longer, then you potentially can put that double bond in more than one location. So position of a double bond in alkene, you've got pent-1-ene, or you could have pent-2-ene. So the double bond occurs on the first carbon or on the second one. Okay. There are no other isomers with 5 carbons. There are, if I sat here and discussed the multiple other isomerisms possible, there are things like if I go into branching, but if I stick to a straight chain alkane, there is only 2 places you could stick that double bond and be different. Okay. Example 2, as I said, we have to study halogenoalkanes in year 12. So again, if you put it on one location and there's another location you could locate it and it be different, then that is called positional isomerism. So if I have chlorobutane, because of the chain being 4 butane, you could potentially stick it on number 1 or 2. Be careful though. There is no such thing as 3-chlorobutane, because what you have to train yourself to do is number from the side. So that again, if you notice, is on position number 2. Okay, be careful. Train yourself to look for the smallest counting position that you potentially can. So moving the chlorine along the chain makes new isomers. So there's potentially 1-chloro or 2-chloro, but there's no 3-chloro. Okay, be careful. Right, in this sense, the molecules have the same molecular formula. They have different functional groups though, and different chemical properties, and as a consequence also have different physical properties. So this means functionality. So sometimes, as weird as it might sound, you might have exactly the same atoms present, but they might be dramatically different functionality. And one of the easiest ones to show this, there's actually my example 2, I should have put it example 1 potential, but example 1, alcohols and ethers. You don't really study ethers in any depth until year 13. So if I go to the second example, ketones and aldehydes, they're both carbonyls, but as I explained earlier, an aldehyde has the functionality terminal, so at the end of the chain, whereas a ketone has the functionality centrally. Okay, so that is called functional isomerism. Okay, another one there, which is acids and esters, which you need to be familiar with. If you look at those, it's got exactly the same number of each atom, so 3 carbons, 6 hydrogens and 2 oxygens, but they're radically different. Okay, and they would behave very differently as well. The next type of isomerism you need to know is stereoisomerism. Now this has 2 main classes, but only one of which you need to be familiar with in year 12. The second one, which is called optical isomerism, we don't touch upon until year 13. Okay, so it's not studied until A2. But molecules often can have the same molecular formula, but the atoms are joined to each other in a very different spatial arrangement. Okay, so they occupy in the VSCPR bit of the syllabus, they would orientate themselves and occupy themselves in a different 3D space. Okay. Right, so geometrical one, which you have to be familiar with in year 12, is called EZ. So it's called EZ and it's linked directly to alkenes. So it's as I said, part of stereoisomerism, but is only found in alkenes. So it occurs due to the fact that a double bond stops you being able to twist it or rotate it, okay? So there's restricted rotation around a C double bond C. So there are two forms of geometric isomerism, two labels you have to be familiar with. The first one, Z, okay, means that you've got atoms on the same side of the double bond being similar. And I'll explain to you what I mean by that in a minute. Okay, so a Z1 means you've got a double bond here in the central, which has a limited rotation, so you can't twist it around. Okay, so you can't take that and make it go rotate around, because that it's a bit like handcuffs. You've put handcuffs on a person. If you handcuff both hands together, then you can't untwist the hands. So if you have, therefore, within that restricted structure an inability to twist, it makes a difference then whether you place these functionalities at the top or the bottom of that double bond. So here you can see that I've placed both similar functionalities at the bottom. Okay, so they're both at the bottom or both at the top, whichever way you want to look at it. That represents, therefore, a Z isomer. Okay. The second one has them on opposite sides. So if I show you the equivalent but an E isomer, again, we've got this limited rotation centrally, so you can't rotate it around that double bond. Okay. What that means is that if I now choose to put the functionality on the left-hand side at the bottom, and on the other side of the double bond, I choose to put the functional or similar bond, similar functionality at the top, then they're opposite to each other. So they're on the opposite sides across the double bond. That represents an E isomer. Now, easy isn't easy, which drives my year 12s mad, but that's the reality of it. Okay, so you need to be clear about what rules help you determine, is it E or is it Z? And sometimes, irritatingly, it's neither. Okay, sometimes EZ isn't possible. And there is a clear rule, which I'm hoping you will remember after tonight, to help you determine yes, no, is it E, is it Z? Okay, so just to be clear, all of this comes out of the fact that you can't twist a C double bond, C. Okay, so in single covalent bonds, so in saturated compounds, you can take that C single bond C and twist it around quite happily. So you can cause it as the yellow arrows there hopefully represent. You can just twist it. So even if it starts its journey at the bottom here, you can take it and twist it around and it will locate itself anywhere you want. So by the end, it could actually be on the top. Okay, but you can twist it back again and be back to what you started with. So in a single bond between two Cs, this isn't going to be an issue because you can twist it into whatever location, top, bottom, side, left, right, whatever. There's easy full rotation potential. However, if you've got restricted rotation, which is the case in any unsaturated bond, so a C double bond, then that is acting like a handcuff on the two carbons and it keeps it in situ. So it freezes them in a single position. Okay, and it's not easy therefore to flip between one and the other. So in this sense, if you represent it and it's currently at the bottom there, then there's no way of you being able to twist it and somehow get this to be at the top. So they're frozen and they're in situ. Okay, so in this sense, easy for geometric isomers, there are rules for you to be able to represent them. Okay. Z, you don't need to remember the German words, I'm glad to say. So Z means that the high priority group's atoms are on the same side, and E means they're on opposite sides of the C double bond C. Okay. So example 1, you can see I've got a big chunky group at the bottom, but if you look at the other side, the chunkiest group is at the top, so opposite, so represents an E isomer. In this one, the chunkiest or heaviest one is at the top, but as is the case here, the big chunky one is at the top again. So that represents a Z isomer. Okay. So how to tell if it exists, if at all? Okay. If you've got two different atom groups either side of that double bond, then you are for sure going to have the potential for an EZ isomer to be shown. Okay. If you've got two similar atoms, but they're both on the same side of that double bond, so in this case, 2 greens and 2 whites, because they're not a green and a white either side, that means that easy is not possible. So you don't have geometric isomerism in this case. In the same sense, I've got different here, green and a white, but the fact that one side of it has identical group attached to it means that we are now limited in our ability to have a easy isomer potentially showing. So anytime you got 2 of the same, so in this case 2 greens, it means that easy cannot exist. Okay, it could be as complex as having 4 things, different things attached. In this case, that will always be easy. Okay, so I'm hoping that you've now got a decent grasp of isomerism from what this session has shown you. If you go on the resources that will be available after this session, what you will see is that there are past paper questions. Okay, if I quick through them, so it's only I was there, and if time would have allowed, I've gone through a few. But take the time at the end of this PowerPoint, look at the past paper questions. You'll be pleased to know that after each question, immediately afterwards, I've placed the mark scheme so that you can self-assess and go through them at your own pace. Okay, so I'm hoping you found that useful, and next week, as I said earlier, I will be revisiting in a bit more in-depth organic chemistry again. So hopefully you'll rejoin me next week.